Hello, and thank you for taking the time to listen to my presentation. My name is Chris Holmes, and I'm going to discuss some recent work researching and characterizing marine emissions from sewage treatment plants and how we've expanded that knowledge into a global perspective. I'd like to acknowledge my co-authors and their affiliations, which are listed on this slide. As we know, many of the substances we use in or around the home and those we ingest, like pharmaceuticals, can be transported via wastewater collection and treatment pathways. After treatment by sewage treatment plants, or STPs, effluent is often discharged to surface water, for which we have a variety of exposure models suited to estimate environmental concentrations. However, direct emission from STPs to marine water are generally not well characterized or geolocated, so marine exposure scenarios are often simply a variation of freshwater scenarios, perhaps with a higher dilution factor applied. This is an area for improvement in environmental assessments. We know that from earliest times people congregated in settlements along the coasts, and over time these have grown to large cities where the population density is often greater than inland population centers. And the trend for population has been shifting from rural to urban areas. So understanding marine emissions will be more important as time progresses. Our aim was to develop a global scale data set centered on marine emissions. We want to estimate as best as possible what fraction of populations are served by STPs discharging directly to coastal waters. There are some data sets of individual STPs that specify the discharge type, like freshwater, marine, land, water reuse, and others. We wanted to learn from those data and extrapolate this knowledge to other parts of the globe where we don't have that detailed information on STPs. Ultimately, this information will be included in exposure models to predict concentrations and eventual risk in aquatic systems, both by refining freshwater scenarios as well as developing more refined marine model scenarios. We identified and acquired a set of 7 databases on STPs suitable for this activity. This covered 34 countries, encompassing over 44,000 STPs and over 1 billion people served. While each database contained a variety of attributes for each STP, we compiled a core set of attributes common across all databases. The geographic location was critical, as we will link STPs with other georeference data as part of our training and extrapolation process. Knowing the population served and effluent flow help us characterize the STPs, and of course the discharge type tells us what type of environment the effluent is ending up in. Overall, for the roughly 1 billion people served across our 44 countries, 13% of the population are served by an STP discharging directly to the marine environment. Other discharge types include estuaries, freshwater, land, water reuse, and a small set of other categories not related to marine discharges. I mentioned that geographic location was important. In addition to knowing the location of STPs, we have geospatial information about rivers and river basins, coastline, population grid, and other anthropogenic aspects. All of these are global data sets and consistent in content and scale across all countries, and this is how we'll extrapolate from one country to another. I don't have time to discuss all the geospatial aspects and processing, but we developed data sets that link STPs to rivers and calculated total hydrologic distance and travel time to the coast for each STP. Here are a few takeaways from that linkage. For all the 34 countries we had STP data for, that's the dark red plotted line, about 22% of the population is served by an STP within 10 kilometers of the coast by river. But when we look at specific countries, like Brazil and Mexico, we can see differences in the way populations served by STPs are in relation to the coast. This helps us develop a more refined understanding of coastal emissions. Based on river travel time, we can also look at population served and how long it takes that effluent to get to the coast. This might help inform marine exposure models, not just from direct emissions, but also what might be coming down from upstream. Simple degradation over time can be applied to these data to estimate mass of a substance reaching the coast. Again, we see differences by individual countries. But the really interesting part is taking what we can quantify for these 34 countries, our training countries, and apply that to a country somewhere else, using that globally consistent spatial data I mentioned. Because in reality, The number of countries that have individual STP locations and associated attributes is quite limited. The first step is to characterize what we know for the training countries using the globally consistent spatial data. The most important is population for each 1 kilometer grid square. This tells us how many people live in each square kilometer across the globe. The first part of that is to allocate the 1 kilometer gridded population to the STPs, using the population served as the limit to how many of those 1 kilometer grids are assigned to each STP. This was a spatial operation and assumed that population closest to the STP are more likely to be connected to that STP. There are clearly other factors and ways of making this connection, and if we were examining just a single country or city, data for this association might be available, but not at the scale we're working in. Once all the STPs are full, the remaining population are considered to be not connected to an STP. Then we can characterize that connected population by their distance to the coast. Even better, we can do that characterization according to the type of STP discharge. For example, in Brazil, 50% of the connected population to a coastal water discharge STP are within 5 kilometers of the coast. The chart on the right shows how coastal water and freshwater connected populations compare for Brazil. This will be different for each country, or even subgroups within countries. For example, we might want to analyze a subset of counties or states as a group. We can also look at the proportion of population served by different STP discharge types and distance zones. For example, here each distance zone is 1 kilometer wide, and we can see how the percent of connected population changes as distance zone increases. For Brazil, the population that are between 4 and 5 kilometers from the coast, 28% are discharging to coastal waters. This number drops to only 1% of the population between 19 and 20 kilometers from the coast. The dramatic shift from coastal to freshwater discharge can be seen between 15 and 20 kilometers, where after that point there is very little population served by a coastal water discharge STP. Similar information can be viewed in a cumulative perspective, rather than by unique distance zones or bands. Once we've characterized the population, what kind of STP they're connected to, and their distance to coast, we can apply that to other selected countries. This is done by linking distance zones between countries, assigning population and distance zones to discharge types, and then summarizing the result. Here we're showing Brazil on the top. This is our training data. On the bottom is Ecuador, for which we don't have STP location information. But we do have global population and distance to the coast for Ecuador. So based on the population in Brazil and which type of STP they're allocated to and their distance to coast, we can assign that same percent of population to the target country. For example, in Brazil, 28% of the population between 4 and 5 kilometers from the coast, which are served by STPs, are served by coastal water STPs. We can apply that same 28% to the STP connected population in Ecuador, which are 4 to 5 kilometers from the coast. Then we can summarize the coastal water served populations in all distance zones and report the STP connected population discharging to coastal waters. Once summarized, we can look at the results of this extrapolation by country, some of which are shown in the table below. But we can also subgroup the results at various spatial levels or by spatial units in order to organize results consistent with existing exposure models so they can be directly utilized. I know this was a lot to cover in 12 minutes, and there are actually a number of other aspects we've used for refining the process, including using urban and rural population designations, per capita GDP for the linking of data, or filtering of training data using spatial or other attributes. Actually, any attribute that we can characterize globally can be used to refine the linkage between population in a training country and population in a target country. We're currently working on methods of evaluating the extrapolation using STP data gathered for individual cities, which weren't included in the training data. And of course, there are a number of assumptions and uncertainties with this process, which need to be made clear and understood before utilizing any of the results of this work. questions like how to best choose the training country, how similar are demographic and wastewater treatment between training and target countries, and are there other factors impacting the similarity between training and target countries not accounted for? Ultimately, knowing proportions of populations served by coastal discharge STPs will be incorporated into existing models that have been used by Unilever for emission and exposure assessment, both to refine freshwater emissions as well as characterize marine emissions at a spatial scale. We've shown how we've acquired data for 34 countries and over 1 billion people served by STPs, and how we can extrapolate that to other areas around the world. And we can use a variety of associations and attributes for that, like per capita GDP of the population, or whether the population is classified as urban or rural. This not only informs marine emissions, but also refines freshwater emissions, since previously it was assumed all STP emissions went to freshwater. We feel this is a step forward in understanding global scale marine emissions. And as a result of the work, we've also developed a useful global data set describing the hydrologic travel time to the coast for each river segment. Ultimately, we must balance the realism incorporated into this process with our ability to apply this in a practical manner at a global scale. Our next steps are to publish the work we're doing in 2021. Thank you for your time and attention.